Okay, so today we are finally going to see the proof of this result. So we have already seen the statement, but let's just again go through it once more briefly. So we have a linear operator T on a finite dimensional vector space V over the field F such that all the characteristic roots, all the distinct characteristic roots of T lie in F, and these are the characteristic roots. Then V has a basis in which the matrix of our operator T has this form, where it's a block diagonal matrix and the number of blocks is equal to the number of distinct characteristic roots, and where each block Ji looks like this. That itself is a block diagonal matrix, and where these blocks are basic Jordan blocks belonging to lambda I. I mean, if for that I, these are basic Jordan blocks of possibly different sizes belonging to that same eigenvalue, I mean a characteristic root lambda I. So let's now see how we can prove this. And in the proof, the author starts by noticing that a basic Jordan block is actually, it can be expressed in terms of another matrix that we have already come across, we have already defined. So he writes, note that the M by M basic Jordan block is just this matrix. Plus MM, where MM is the M by M matrix where almost all the entries are 0 except the entries on the super diagonal, the diagonal that lies above the leading diagonal, and there all the entries are 1. And we defined these matrices MM when we were studying nilpotent operators. If you remember, and we did this at the end of lemma 652. So that's what the author also writes, as defined at the end of lemma 652. For example, so this is not a part of the proof, so I am just simply showing you. Say you want to write M4, okay, so it will look like this. So this is your M4. All the entries are 0 except, so this is the leading diagonal, this is the leading diagonal, the super diagonal consists of 1s. So those are the only non-zero entries, elsewhere it's all 0. And IM of course is the M by M identity matrix. And do you see why this is true? Because that's how a Jordan block has been defined. A Jordan block, a basic Jordan block almost looks like this, except we have lambdas here, not necessarily 0. We may have 0, but in general we have lambdas. So obviously a basic Jordan block can be written like this, lambda times the identity matrix of that size plus MM. Alright, and next we go back to one discussion that we have already had about simplifying this result. You remember that we were considering the minimal polynomial of our operator in a previous discussion, in the previous video I think. And we considered the factorization of the minimal polynomial as a product of powers of irreducible polynomials, where all these qix's are irreducible over f and these li's are positive integers. And this led to a decomposition of the vector space as a direct sum of subspaces invariant under T, and we were able to consider the restrictions of T on each such subspace Vi, and we recognized the fact that whatever we are trying to prove here actually can be done for those individual Ti's, and it's enough. Okay, it's enough if we prove this entire thing for only those Ti's. Now, what type of operators are Ti's? Ti's are somewhat special. Just like Px is the minimal polynomial for our original operator T, this is the minimal polynomial for T1, this is the minimal polynomial for Tk. So, by that discussion, it's enough to prove our result only for operators which have minimal polynomials like this. But another thing is also true. Don't forget that now we have the additional assumption that all the characteristic roots of T lie in F. And in that case, these irreducible polynomials become linear. They look like this: x minus lambda 1 and so on, x minus lambda k. So, it's enough to now prove the result, or it's enough to assume that our T is an operator whose minimal polynomial looks like this, this or this. That means that our operator now has exactly one distinct eigenvalue. For example, say the minimal polynomial of our T now is going to look like this. Then obviously, if you replace x with T, you are going to get the 0 operator. So, you will have this. Let me just simply write it as lambda, or let me write lambda 1. You will get the 0 operator. What does this equation tell you? Because L1 is positive, this equation tells us that the operator T minus lambda 1 is nilpotent. And that's how the entire thing gets reduced to the case of a nilpotent operator. Of course, T itself may not be nilpotent, but T can be written as lambda plus T minus lambda. Oh, and one more thing, do not forget that when we add or subtract simply lambda, it's not just the scalar lambda, but lambda times the identity operator. That's understood. Now, from the previous section, you know how the matrices of nilpotent operators look, and in those matrices these mi's appear as diagonal blocks. So, there we have the connection, and we are now going to use that connection to find the type of matrix that T will have in some basis. Okay, so that's the plan. And now if we write this entire thing systematically, it will look like this. We will have to refer to the relevant results that will justify this simplification. And the author writes, by lemma 651. You can go back to these results and see how they justify this simplification. And the corollary to Theorem 661. Six five one means the previous section on nilpotent operators. That result and the corollary to Theorem 661, which we have seen in this section itself, it's enough to assume that T has exactly one distinct eigenvalue, characteristic root. It's not entirely correct to simply write T has exactly one characteristic root. That may be wrong, but it has exactly one distinct characteristic roots which may be repeated depending on the dimension of the underlying vector space V. If it has dimension n, then T will have, say if we are calling this characteristic root lambda, n times it lambda will appear. Then, or we can write so, T minus lambda is nilpotent. We have already seen just now how that is true. And now we can apply the result of nilpotent operators here, and that result was Theorem 651. Hence, by Theorem 651, V has a basis. In which the matrix of T minus lambda is of the form this. Mn2 MnR. Recall your previous section result. Since T is equal to lambda plus T minus lambda, the matrix of T in this same basis is of the form this. These two matrices are of the same size. Okay, if this is n by n, this is also n by n, and it's the diagonal matrix. Actually, it's a scalar matrix where all the diagonal entries are lambda. And whenever, I have already said this before, the places where we do not write anything in a matrix, it's assumed that those places are 0. But you have to interpret this carefully. The sizes are same. This is a block diagonal matrix where the blocks are not necessarily 1 by 1. They may have larger size. Here, however, these lambdas are individual entries. So, although the sizes are equal, you cannot make this lambda correspond to mn1, this lambda corresponding to mn2. You cannot think like that. If, for example, the size of mn1, in fact, if n1 is equal to 2, then you have to consider these two lambdas, and together they will give you a 2 by 2 block that will correspond to this one. Okay, so like that you have to make the link, because now you are going to add. Oh, and one more thing, why are we getting the matrix like this? That's because the operator algebra and matrix algebra are isomorphic. So if you find the matrix of this in some basis and the matrix of the operator lambda times identity operator in any basis is going to look like this. If you have these things, then the matrix of T is simply the sum of the matrices of these two things. Okay, so that comes basically from that fact that operator and matrix algebras are isomorphic, and that too an operator which corresponds to a corresponding matrix, that itself gives the isomorphism. So now if you do the addition, what will you get? You will get this. B n1, B n2, B nr, where these are basic Jordan blocks corresponding to lambda. Do you see how you are getting this B n1, for example? You will choose n1 lambdas from here and think of that diagonal block. That gets added to mn1. So what does that do? The sum is bn1 because the lambdas appear, that n1 number of lambdas will appear along the diagonal of bn1, diagonal of bn1 only. And in the super diagonal, you will have the ones which are coming from mn1. Elsewhere it's 0, and that is how you get a basic Jordan block. Similarly, you will choose another n2 lambdas to create bn2 combined with mn2, and like that it will go. So you see that all these Jordan blocks belong to that same characteristic root lambda, but they may have different sizes. So that's how you get bi1, bi2, those things. Okay, so that's just it. I mean, this is the case where T has only one distinct characteristic root. But if we consider the original case, then obviously these matrices will appear as diagonal blocks in the matrix of the original entry, and that is how in fact we are able to have this simple case, simplification, where T is somewhat special. So if you combine all these matrices, you can think of our T now as a Ti there in the general discussion. So if you combine the matrices of Ti, put them along the diagonal of that large matrix, which should be the matrix of that general T, then obviously that's the result. Okay. So actually this is the proof. Yeah, that's just it. And now one final thing. The basic Jordan blocks may not appear in a decreasing order in terms of size, but you can do so by rearranging the vectors of your original basis, the basis of the entire space V, by rearranging the vectors of the basis of V. I said the basis because the basis that appears in this proof. Or you can say vectors of the above basis of V. If necessary, we can have a decreasing size of Bn1 greater than or equal to size of, or if you are talking about the general result, you can in fact write that notation, size of Bi2 and so on. With this, the final matrix of T, which has those Ji's, has a name. It's called the Jordan form of T. We specify this order to make that matrix unique. This matrix is called the Jordan form of T. Now, one thing is clear, it's obvious from all this discussion that we have this. For two operators in our algebra, both of which have all their characteristic roots, let me write in short as CH roots, in F. Are similar if and only if they have the same Jordan form. So the Jordan form determines the similarity class of this type of operators. Similarity classes, of course, there may be others also uniquely. Which just means that if you have one Jordan block, one Jordan form, a matrix of that form, then it will determine exactly one similarity class. From where, if you choose any operator, its Jordan form will be exactly that. Okay, so it kind of determines that similarity class. But of course, your operator should be such that all its characteristic roots should lie in F. The general situation where this is not necessarily the case, that we will discuss in the next section in rational canonical form. After this, there is a small discussion on the matrix version of all these things, which however is so easy that I leave that discussion to you to understand. It is in fact easier than the operator version. That's because the original operator version or the original result, the one that we proved today, is ultimately about matrices. So here you have to go from operators to matrices, but that one is just about matrices itself. The objects themselves are matrices. So with that, this section is over. Now after that, we will start solving the exercise problems. So this video ends here itself, and tomorrow of course we again have analysis. So that's just it for tonight. See you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.